Hey, welcome back to Bow Maths. You like fabric? Good, because we're going to be using it today. Well, hello everyone, and as you might have guessed, today we're going to be talking about fabric. But in order to do that, let me just kind of do a little bit of setup first for what this is going to be about. We've been talking about greatest common factor lately, and I thought, well, this would be a really cool application to show you where greatest common factor might actually get used in real life. So to do that, let's discuss what a square is. All right, so what is a square? Well, you could tell me, hey, this is a square, right? And if you know a little bit about squares, you'll know that all the sides are the same length. So if this is like 3 centimeters, then it's 3 centimeters all the way around the square, right? In contrast to that, just a general rectangle, it doesn't have to be the same length as it is the width, right? This could maybe be 4 centimeters, and this could be 3 centimeters, right? Right, so a square is basically a rectangle, but where the width and length are the exact same as each other. All right, so now this is really all the context we need. What I'm going to do now is I'm going to say, all right, I have this piece of fabric here. All right, nice brown piece of fabric. And what I want to do is I want to split this up into a square. I want to make a square out of this. Now, if I measure this, I'll see it's about 30 centimeters along the top and roughly 20 centimeters along the side. All right, so we can draw this out. We get a rectangle that's 30 centimeters on the top and bottom and 20 centimeters on the sides. But I'm saying, hey, I want to make this into a square. So one thing you could do is think, okay, well, a square has the same side length. So if I just maybe go along 10 centimeters into this rectangle here and I chop this piece off, I'll be left with a 20 centimeter by 20 centimeter square. But the problem is that's wasteful, right? Like we'll just have a little piece of fabric left over, and we want to try and maximize the amount of fabric that we use. We don't want to just be chopping off fabric and throwing it in the trash willy-nilly, right? So my problem for you is, given this piece of fabric here, how can I cut it into squares such that I'm not going to waste any area, so I'm not going to waste any of the fabric, and that these squares are as big as possible? What this is going to equate to is basically us taking this and trying to split it up into squares. Right, so I can split this up into a bunch of squares such that literally all of the area of this fabric is covered by squares, which means that when we cut it out, we're wasting no fabric and we're going to get a bunch of squares. However, the further caveat is that we don't want these squares to be absolutely tiny, right? We want these squares to be as big as possible. And so this is where our problem of greatest common factor comes in. All right, so I know the top is 30 centimeters. Now I could maybe cut out one centimeter squares, right? So that means I'd be basically taking 30 cuts along the top. And then if the squares are going to be 1 centimeter by 1 centimeter, that means I'm doing 20 centimeters along the side, or 20 cuts along the side, right? If I'm doing it into ones. But maybe I can do a little better than that. What if I did 2 centimeters by 2 centimeter squares? Well, that means, okay, 30, that's 2 times 15. So I could cut along the top 15 times, making a cut every 2 centimeters. And I'd cut along the side 10 times, making a cut every 2 centimeters, right? Because we're splitting it up into 2. And so 20 divided by 2 will be 10 cuts. But again, is this as big as we can get for the squares? And then I could try maybe 3, right? So I could go along the side 30, that's 3 times 10. So 3, I cut every 3 centimeters, so that would be making 10 cuts. But if I try and go along the 20 side, is 3 a factor of 20? No, it's not, right? 20 is not divisible by 3, so I'd go 3, 6, 9, 12, 15, 18, but then, I'm at 21, right? I've skipped over 20. So it doesn't go into 20, so I have to basically cut them into a length that is a common factor to both of them. And furthermore, since I'm trying to get the biggest possible square, it's got to be a greatest common factor that we're looking for. So that is exactly why greatest common factor is going to be relevant here. We're trying to find the biggest possible squares. We're looking to basically divide this 30 into some sort of factor and this 20 into the same factor, because a square needs to be the same length on both the height and the width. And in order to do that, we get a common factor. And to make it the biggest possible square, that's the greatest common factor. All right, so now that we've done that, we know how to find the greatest common factor, right? We've been doing that the last couple videos. So let's do this. So we have 20 and 30. So I'm going to split up 20 into 4 and 5, 5 is prime, and 4 I'm going to split up into 2 and 2. Alright, so the prime factorization of 20 is 2 times 2 times 5. Now I'm going to do it with 30. So 30 I can split up into 6 times 5. 5 is prime, and 6 I can split up into 2 times 3. So I get the prime factorization of 30 is 2 times 3 times 5. Now if I go ahead and circle the common factors, we see that they both have a 2 common, and they both have a 5 common. Alright, so this means that the greatest common factor of 20 and 30 is going to be 2 times 5, which is 10. So that means every 10 centimeters, so on the top I'm going to do it 3 times, right, because 30 divided by 10 is 3, and along the sides, every 10 centimeters, so I'm going to do it 2 times because this is 20 centimeters in total. I'm going to also make a cut. That's going to basically split this up into perfect squares where I've wasted none of the material. So along the top, I'm going to make a mark every 10 centimeters. All right, so 0 to 10, 10 to 20, and 20 to 30. And along the side, I'm going to make a mark every 10 centimeters. So 0 to 10, and then 10 to 20. All right, so what this means is that if I cut along this, if I cut along these, I'm going to split this up into, by the looks of it, 6 squares. And those squares are the biggest possible ones we could have done for this piece of fabric. So let's go ahead and cut this up. All I did with that little device was basically just kind of make a little grid so that I can follow with my scissors easier. So let's go ahead and do this. And there you have it, folks. I just split up that piece of fabric into 6 squares, wasted no fabric, and I got the biggest squares possible, all thanks to our buddy, greatest common factor. Now, this is just a cute little application of it, right? And you can see that this will work for any shape of fabric you have. As long as you have a rectangle, you can measure the sides. You just find the greatest common factor of those sides, and that's the length of your squares that you're going to cut it into. And this doesn't just apply to fabric. You could do this for paper, sheet metal, really whatever material you're trying to cut squares out of. And this is going to give you the biggest possible squares. You're going to have no waste left over. And it's all thanks to math. Prime factors, greatest common factors, all that jazz. So I hope you found this little application kind of interesting. I think it's really cool. And yeah, that's going to be it for today. Have a good one. Stay groovy. And I'll see you in that next video.